Hi again everyone, Dr. Tom McNamara here for our course in trigonometry. In this video we are going to talk about finding areas of sectors of circles. Okay, so let's just start out with a quick picture here so that we all know what's going on. Okay, so that's not a terrible circle. I'm getting a little better at drawing these circles. So what I mean when I say the area of a sector. Okay, so we have a central angle sitting in there, some angle theta. Now, in the last video we were talking about arc length. So that was the distance, if we were traveling along the circle, the distance from here to here. When we're talking about the area of a sector, well, we're talking about the area of this little pizza slice right there. Okay, so let's just think about how we could figure something like this out, and we're going to try and relate this to the central angle. Okay, so we know for the entire circle, the area is pi times the radius squared. Okay, so let's imagine not an entire circle, but I don't know, a 60-degree central angle. So find the area of the sector described by a 60-degree central angle. Okay, so let's go back and use this picture right here again. Okay, so let's imagine that is 60 degrees. So if I go around the one full revolution, in other words 360 degrees, I'd get the whole circle, pi r squared. Okay, but I've only gone around 60 degrees, so the area of the sector should be proportional to how far I've gone around. Okay, so the area that I want, the area of the sector described in this picture, should be 60 degrees over 360 times pi r squared. Okay, so pi over 6 times the radius squared. Okay, now you'll remember pi over 6 is one of our special angles in radians, but pi over 6 does not correspond to a 60-degree angle. There's a little bit of a trick that we need to do here. What you need to do is take 1/2 your angle in radians times r squared. Okay, so you take your angle in radians times r squared, cut that in half, and you get the area of the sector. Okay, the reason is that the formula for area of a circle doesn't have 2 pi in it, it only has pi in it. Okay, so let's keep that in mind while we do a few of these problems here. So the area of a sector is 1/2 r squared theta, and once again, theta needs to be measured in radians. Okay, theta needs to be measured in radians. Okay, let me pull an example problem here out of our textbook, and give me a nice, maybe a nice applied problem about area. Ooh, here's a fun one about a windshield wiper. Okay, so we're imagining that an automobile windshield wiper is 10 inches long and it rotates through an angle of 60 degrees. Okay, so from here to, oh, I don't know, about there. Okay, something like that. So we're going to rotate through an angle of 60 degrees. Now, here's the little complication. I don't want to know this entire wedge. Okay, so if you look on your car's windshield wipers, the blade doesn't cover the entire wiper arm. So we're going to pretend that the windshield wiper covers 9 inches of the wiper blade. Okay, so in other words, this will be the area of your windshield that is not cleaned off by the wiper. So the question is, how much of the windshield is cleaned? In other words, what is the area cleaned by the wiper blade? So 60 degrees, we know that's pi over 3 radians. Okay, so here's the idea. What we're going to do is we're going to find the area of this entire wedge-shaped region, and then we're going to do a subtraction here. Okay, so the area of the large outer sector. So, what we're going to do is we're going to apply that right there. 1/2 r squared theta, so 10 inches squared times theta, which is pi over 3. So I'm getting 100 pi over 6 square inches. Okay, don't get thrown off and don't square this. Okay, inches squared is a unit of measure. It's a square, side length 1 inch. So we know that we're measuring area since we're talking about inches squared. Okay, so that's this entire wedge. Now I don't want that whole thing. I want this part only. So we're going to take away the area of this little sector in the corner. Of course, to do that, we're going to need to find the area of the little sector. Alright, so once again, 1/2 r squared theta. Now that has radius 1 inch. And theta is still pi over 3, so this is pi over 6 inches squared. Okay, so the area cleaned off by the wiper blade, which is here, we can find that by doing a subtraction. Okay, we know the area of the entire wedge-shaped sector, and we know this area. So if we take the area of the entire wedge-shaped sector and subtract off that little part, it'll give us the shaded region that we're looking at. So the area cleared by the wiper blade, well, you do 100 pi over 6 minus pi over 6. So I'm getting 99 times pi over 6. 33 pi over 2 inches squared. If you look back in the section where we started talking about radians, we talked about how to do these calculations where your expression involves pi. You're doing it with fractions here. They've already got a common denominator. So you just deal with the numerators. This numerator should be thought of as 100 pi. So you got 100 pi minus pi, 99 pi. Where did this 33 come from? Well, each of these guys are divisible by 3, so that factor of 3 cancels out. And you're left with 33 over 2 pi square inches cleared off by the wiper blade. Okay, so a couple of nice applications of the formula for the area of a sector of a circle. So we got two important things. Formula for the area, or formula for arc length, S equals r theta. Formula for the area of a sector, area A equals 1/2 r squared theta. And in both cases, theta should be measured in radians. If you try to do it in degrees, you have to convert to radians anyway. So if you look back at the example we did at the very start, that's what we ended up doing. So it's just best to measure the angle in radians right from the get-go.